Okay, so welcome back, everybody. I hope you had a nice lunch. So we go back to physics, and the first speaker is Masazumi Onda, telling us about quantum error corrections and lattice gate theory. So, thank you.
Thank you for the introduction and giving me opportunity to talk about my research here. Also, sorry for not attending the first part of this workshop because I'm also one of the organizers of another workshop in YITP. So I decided to attend the two workshops half. Okay, I'm Masazumi from iTHEMS, and I'm doing a senior research scientist in iTHEMS. Today, I'm going to talk about the quantum error correction and lattice gate theory. This talk is based on our collaboration with these guys, basically from us. Okay, let me start with the introduction. My main background is high energy physics, and 7 years ago, I was a postdoc in Cambridge, and then I started to work on application of quantum computing to numerical simulation of quantum field theory. Then I imagined a future like we can simulate what actually happens in accelerator, universe, black hole, and so on by using quantum computer. And I still imagine such a future, and but when I started this topic, my feeling was like I just wait for development of hardware of quantum computer, and then later I will apply that development for high energy physics. But after getting understanding status, I realized that this is not so easy. And so my feeling is like quantum computation is a promising approach if there is a sufficient computational resource to do problem under consideration. And actually, in my understanding, there are big two challenges. One is to get a sufficient number of qubits to implement quantum error correction to do a fault-tolerant quantum computation. Another challenge is specific for my purpose. Actually, formulation of quantum field theory is quite intricate, and especially gauge theory is important for understanding high energy physics. And another challenge is that to find an efficient way to put gauge theory on quantum computer. And today I'd like to talk about something I noticed or I understood. The topic of this talk is about possible relations between quantum error correction and gauge theory. So a priori, they seem to be two different frameworks, but somehow they are connected or even they are the same. This is our result. Okay, but before explaining our result, let me list up some motivations to think or wonder about the relations. And first motivation is that there is already an explicit example for that relation. In quantum error correction, there is a famous error correcting code called solid code. Actually, it is known that this can be understood as some lattice gauge theory with D2 gauge group. I will elaborate this point later. And another motivation is very important in this talk. Actually, it seems there is a conceptual similarity between quantum error correction and gauge theory. I will also elaborate this, but actually quantum error correction is a kind of a description of logical qubits using more qubits called physical qubits. So it's a redundant description of logical qubit. And gauge theory, usually in gauge theory, we start with larger Hilbert space, including not only physical states but also unphysical states, like a photon with a longitudinal wave or something like that, longitudinal polarization. So in that sense, gauge theory is also a redundant description of physical states using more states. And third motivation is not logical, only intuitive. We know that nature is, to some extent, nature is described by gauge theory, but nature could be also considered a quantum computer. In that sense, gauge theory may know something about the quantum error correction itself. And final motivation is that there are already proposals on relation between quantum error correction and concepts in high energy physics, like holography, black hole, conformal field theory, and normalization group. And our work is adding one example to this kind of proposals. Okay, this is a motivation. And here is a list of main results which I will explain in details. Actually, so now I think that rather than having a relation, now to some extent, quantum error correction itself can be regarded as gauge theory can be regarded as a quantum error correcting code. And first result is that we show that lattice gauge theory, any lattice gauge theory with abelian gauge group can be interpreted as error correcting code. And we also constructed two types of codes, which are called Gauss law code and vacuum code. And in Gauss law code, in gauge theory, physical states are subject to a condition called Gauss law, and we can regard the Gauss law constraint as a stabilizer condition for error correction. In vacuum code, we add another extra constraint coming from fixing matter charge or fixing conserved quantity. And also we found that cases with matter can be interpreted as a class of code called subsystem code. Also, property of error correcting code for generic case, it's very complicated, but we also found that the property is transparently explained by using framework called quantum reference frame. But I will explain this point only briefly. And this is a summary of a dictionary for the correspondence between error correcting code and gauge theory. Left-hand side, for quantum error correction side, we have errors, logical qubit, condition not to have errors, logical operator, and so on. And in gauge theory, we found that these concepts correspond to these concepts. For example, errors correspond to unphysical operators, and logical qubit can be identified with physical states in gauge theory. And stabilizer condition is identified with the Gauss law, and the logical operator corresponding to gauge invariant operator. So this is our main result. Okay, so now I finished the introduction, and next up, I will give details of some important points to explain my main result. Okay, let me start with a brief explanation of quantum error correction. And although I didn't attend the first day of the workshop, but the first day had many talks on quantum computing. So I'll skip some basics of quantum error correction, and I'll just explain what is needed to explain our results. So in quantum error correction, in particular in so-called stabilizer formalism, first we consider larger Hilbert space by encoding procedure. So suppose that we would like to do some computation in Hilbert space H, but when we take into account quantum error correction, we consider larger Hilbert space. And then error can act somewhere in this Hilbert space, and we have to detect errors by some way. And in stabilizer formalism, we detect error by measuring eigenvalues of some set of operators. And in appropriate choice, so we regard there is no error if all the eigenvalues of the set of operators is 1. Then we can have estimation on where errors are active. Then based on this guess, we do error recovery. So meaning that ideally we would like to act inverse of the error based on the distribution of eigenvalues. And the important point here is that we start with a larger Hilbert space, and then we constrain Hilbert space by imposing some constraints on the eigenvalues. Next, let me also briefly explain what lattice gauge theory is. Easy seen from the name, lattice gauge theory is gauge theory on lattice. And we put degrees of freedom corresponding to gauge field, usually on links of lattice, and we usually put matter on side or vertex of lattice. And because of the because this is gauge theory, there is a condition on physical state called Gauss law, and this equation is like one of Maxwell's equation, and we have to consider quantum version of this operator version of that equation. And in continuous theory, this is described by using a derivative, but on lattice, this is described by difference. But anyway, there is a counterpart of the Gauss law constraint on lattice. Important point is that we start with larger Hilbert space than state of physical state, and then we give a constraint on Hilbert space to describe physical state. And so now I can explain a bit more detail on conceptual similarity on these two frameworks. Quantum error correction is a redundant description of logical qubits by mod qubit. For example, for the case of 3-qubit bit flip code, we encode 1 qubit in terms of 3 qubits. And for the case of gauge theory, this is can be regarded as a redundant description of physical space by larger state space, including unphysical state. For example, for the case of gauge theory with U1 gauge theory with matter, like electrodynamics with matter, physical states are subject to Gauss law. And let me finalize the motivation part by mentioning this slide. So I'm interested in simulation of gauge theory by using quantum computer. And when we try to put gauge theory on quantum computer, actually there are choices on which part of the states regarded as logical qubits or not, or something like that. And this is connected to whether we start simulation after solving Gauss law or not. For simple setup of gauge theory, we can solve Gauss law explicitly before simulation. For that case, we can regard physical state as a logical qubit. Then we have an encoding for quantum error correction. So compared to physical states, so we should work in a larger Hilbert space. But for generic gauge theory, it's difficult to solve Gauss law. For example, for non-abelian gauge theory, it's not easy to solve Gauss law. And then we have to consider different strategies. So physical state is here, but when we don't solve Gauss law, so we consider kinematical degrees of freedom, including we work in kinematical degrees of freedom, including unphysical state. Then we identify, when we try to do a quantum simulation, we identify this state with logical qubit. But to take into account error correction, we have to work in further larger Hilbert space. So in that sense, in this choice, there is a redundancy in two-fold way. So therefore, in this kind of approach, we need to consider many qubits. So in that sense, naive implementation in that way sound like that we have a more clever way to put the gauge theory on quantum computer. Okay. Then let me go to my explicit example. So first example is the famous toric code. Toric code is described by some quantum system with this Hamiltonian. So here Z means ZE means Pauli matrix sigma 3 on H, and X is sigma 1 on some H. And this is the shorthand notation for the product of Z along the face. And this is shorthand notation for the product of X around the vertex. Then stabilizer condition or no error condition is given by this. So this is nothing but condition for ground state. And this gives the ground state since these operators are commuting each other, and having eigenvalue 1 gives the ground state for this, if J is positive. And then in this code, logical operators are actually identified as a product of X and Z along a non-trivial cycle. And actually there is a beautiful interpretation of this from the viewpoint of topological quantum field theory, but I will not explain details. So this is a very brief description of the toric code. Next, let me interpret this from the viewpoint of lattice gauge theory with D2 gauge group. If I am asked to write Hamiltonian of lattice D2 gauge theory on lattice, I would write down this Hamiltonian. Here, roughly speaking, U is exponential of gauge field or Wilson line, and pi is the counterpart of electric field on G2. But since this is gauge theory, we have to physical states are subject to Gauss law given by the eigenvalue, this eigenvalue equation. And compared to toric code, we have an extra term. But if we consider the case with G equals 0, then ground state condition for ground state is given by the eigenstate of this guy, this operator. And if we identify the basis of this operator with computational basis, these conditions are nothing but the condition for stabilizer condition for toric code. So in that sense, from the viewpoint of gauge theory, toric code has a in toric code stabilizer condition of toric code impose Gauss law, both Gauss law condition and Gauss law condition and minimum energy condition. But Gauss law condition is energetically imposed in toric code. So this is already existing example. Next, let me describe simpler example as a code, but its gauge theory interpretation was a priori not clear. So let me consider a 3-qubit bit flip code. And we have a potential action of a bit flip with some probability. And then we have an encoding of 1 qubit using 3 qubits. And error is detected by knowing eigenvalue of these two operators, D1, D2, and D3. And stabilizer condition and no error condition is given by this eigenvalue equation. And this can be this can be regarded as some sort of simple lattice gauge theory with 3 sides. So let us consider lattice with 3 sides. And on link, we have a degrees of freedom corresponding to gauge field. And usually we have this kind of Hamiltonian. And Gauss law is given by this condition. And this is the same equation. And again, if we identify the computation basis with the eigenstate of these operators, then we get this equation. And this is nothing but stabilizer condition on 3-qubit bit flip code. And actually, correctable error set is simply a single product of X. And logical operator is a product of X along the lattice. And there is an interpretation of this from the viewpoint of what is called quantum reference frame. Let me briefly explain this viewpoint. But because due to time, it's only briefly. So quantum reference frame is a framework to describe physics of, in my understanding, physics of constraint system in terms of relation between degrees of freedom. And here we have a constraint by gauge symmetry. And gauge symmetry generator is given by the Gauss law operator, which is technically given by the product of 2Z. So although we have a priori 3 degrees of freedom, actual independent degrees of freedom are only 2. therefore, among 3 degrees of freedom, we can choose 2 links as a kind of reference frame. And for example, we can take 0, 1 link and 1, 2 link as a reference frame. Or we can do another choice. Then we have a natural splitting in terms of reference frame and system. So we have a tensor product here. And then we can also reorganize the field vector space in terms of logical gauge invariant information or not and other information. Yeah. And HQ is technically given by this operator. Psi L is spanned by physical state 0, 0, 0 and 1, 1, 1, satisfying Gauss law. And HK is defined as the action of X on the state. Then, in terms of this information, we can define a nice map between splitting of information reference frame and logical information. So actually, we can have a map from this Hilbert space, product Hilbert space to a whole Hilbert space. And this is technically given by this. And then whole Hilbert space can be written like this. And from this viewpoint, at this stage, we have a pair of redundant information, reference frame information, and logical information. Then, in this language, action of error has a clear meaning. For example, when we have a single bit flip error, then when we have action of X to this state, we have a change for the only state in HR, but we keep the information for the logical Hilbert space. So therefore, in this picture, when we have action of a correctable error, Hilbert space has a change only for the reference frame part, and we don't have a change for the logical information. So this is an interpretation of error correction from the viewpoint of quantum reference frame. And I also have a more complicated example with matter, but let me skip this and part and conclude my talk. So actually, under some condition, this lattice scale theory can be understood as a class of error correcting code called subsystem code, but let me skip this point. And also, in this talk, I focused on very, very simple examples, but in our paper, we discussed much more general case of lattice gauge theory with abelian gauge group. And actually, using quantum reference frame in that simple example was like discussing a simple one by using a difficult language, but for generic setup, quantum reference frame is actually useful or give a transparent description, both technically and conceptually. Also, we found that when gauge group is a finite group, lattice gauge theory can be regarded as a class of code called CSS code. And code distance of code depends on the details of setup, especially on dimension. Okay, let me summarize. So we found that some class of lattice gauge theory is actually interpreted as a error correcting code. And here is the outlook. So we are also working on improvement of quantum error correction for simulation of gauge theory. And recently we found that by considering duplication of some parts of the gauge freedom, we can efficiently take into account error correction. Also, we are working on extension of toric code from viewpoint of condensed matter physics. Okay, this is the end of my talk. Thank you.
Thank you very much, Masazumi. Questions?
Yeah, so thank you for the interesting talk. So is it so in principle any lattice gauge theory with abelian gauge group, its Hamiltonian can be written in terms of logical operations as a dual description?
Okay, here actually Hamiltonian is not important. Okay, it depends on what we'd like to describe. So we can discuss the argument independent of Hamiltonian, yeah, because we focus on okay, when we consider only Gauss law, Hamiltonian is not important. But when we would like to impose the ground state energy condition as a stabilizer, Hamiltonian is important. So it depends on what kind of code we'd like to consider. Yeah.
Okay, yeah, thank you.
Thank you.
Okay, yes.
So I have a question on your statement about codistance 3 in higher dimension. Can you say more about that?
This one? Good. Thank you. For example, this case, we have 6 qubits, 3 qubits on links and 3 qubits on vertex. And if we regard stabilizer condition purely as a Gauss law, we have this code. But for that case, we can collectible error set with action of x somewhere inside 6 qubits. But therefore, action of operator which is not gauge invariant is regarded as error in that description. But here we change the criterion on which part of the action is regarded as error. So here is so here we further decompose gauge invariant Hilbert space into 2 parts, which involves first one involves only gauge field part, but another part involves also matter. Then in the previous page, we want to protect this 3 qubit Hilbert space. But suppose that we decide that we like to protect only this part. Then we have a structure of subsystem code.
So that applies to the geometry of a loop. Is that?
Yeah.
For general N.
So it can be regarded as stabilizer code for generic. Yeah.
All right. More questions? In the interest of time, let's thank Masazumi again.